you remember that if you remember the basic diagram of the power electronics system, so that there was a power processor, then that has gone to the load, and from there is a controller, and controller will give the control signal, and there is a reference here, and this is your input, and that will be your output. So this is the main part of the power, heart of the power processor. Power electronics is this power processor. That means this power processor. So I want to discuss these things now. What could be inside the power processor, or what are the power processor? In the power processor, there could be, depending on the application, the output to the load may have any of the following in the power processor. In most power electronics, the input is from electric utility circuit. Okay, I am asking you this question. It is written that in most power electronic system, not all, right? In most power electronic system, the input is from the electric utility source. What do you mean by electric utility source?
DPDC, DESCO.
Yes.
This component.
And it is mentioned that most power electronic system. That means not all. So what could be the other? Who will supply who can get you the input?
So power can be generated from solar cells which are located.
Right. From the renewable sources of energy. So from the renewable sources of energy, other than the utility, you can get renewable sources of energy. You can have that input. Like as someone mentioned that photovoltaic, right? Photovoltaic. And say wind generator. There could be some other things. I have already discussed. If not, you can go to the internet, find out different sources of the renewable energy. Okay. And now, depending on your application, the output may be the following. Maybe the DC. If the output is DC, your power processor output is DC, your power processor. If this output is DC, then it could be constant. One could be constant and another could be variable. Variable output. I am talking about the output. That is this output. So where we use the constant? Any example? Can anyone give me what is the where we need that constant or regulated output? Where?
Low voltage electronics.
Yes, okay. Like in your mobile charger,
yes,
from that
the laptop.
charger, you always want from laptop. Okay, that means UPS, you always want IPS, you always want, and also suppose you always want that in a paper mill, you are getting the paper, you want a constant voltage, constant speed of a motor. So the applied voltage must be always constant. If there is a variable, if there is any fluctuation of the speed of the motor, then your roll of the paper will be broken. Okay. So in some cases, we want the constant magnitude, and in adjustable magnitude. Adjustable means that variable magnitude. Like what the example is, suppose you want variable speed drive. That means where you want the speed of the motor would be variable. You want to change. This is intentional. You want to change the speed. There you can use it, and also you can have that this one. This This one could be. This one could be AC. If the output is AC, that output could be constant frequency or variable magnitude. Frequency could be constant, but you may want that variable magnitude in your output, or if you can both, you may want to change the frequency as well as magnitude. In power electronics, this is very much what should I say? It is people are using all these things like your electric vehicle. So, or in the electric train, they change the frequency as well as they change the magnitude. So, okay. So, okay, inside that power processor, actually, inside the power processor, basically what we have inside, right down, inside the power processor, we have converter, power converter. Number 2, energy storage elements. So if I ask you what is the component of the power processor, so you must say that okay, that there could be numbers of or single converters or numbers of converters, and there could be some energy storage element. What could be the energy storage element? Passive type energy storage element. I'm asking question.
So
Sir, it can be passive.
capacitor.
Capacitor inductor.
Capacitor and
Yeah,
inductors.
capacitor and inductor. Look here, 2 students have already left. So they are present at that. I will take the attendance again in the middle of the class. Okay. So don't deceive yourself. Don't teach yourself. You will be the teacher. Okay. So let us have a look of the power processor here. So this is the block diagram of the power processor. I hope you can see it, right? Can you see it?
Yes, sir.
Yes.
So, yeah, input is entering into this power processor. This is the power processor block. So you can use one converter, then some of the inductance or capacitance could be here. That the power energy storage element. And then after that you can use, suppose you are using say AC here, make it DC, and then from DC you can make again AC. There is reason for this one because then this DC to AC you can have variable magnitude of your frequency as well as output. Okay, so we can have the things. We'll go very details in the coming classes. So in the classification way, we can say that in the converter, what could be the converters inside that power processor? AC to DC. AC to DC is the nothing but the rectifiers. So rectifier could be 2 types. One is the uncontrolled rectifiers. Uncontrolled rectifiers. That means the magnitude is, we cannot have any control. That magnitude will depend on the input voltage. But you can have controlled rectifier. In the control rectifier, we shall use special devices. The device is the SCR, or people call it thyristors. We shall come to this device. So there could be DC to AC, and this is also known as the inverter. And DC to DC, your times are speaking you, and this is known as the chopper also. There are different types of DC to DC converter. Buck converter, boost converter, buck boost converter, tube converter, right? Have you heard the name? Okay.
Yes, sir.
Yes.
And then there could be some AC to AC converter. We call it AC regulator. AC regulators are used in your home, like in your fan. you are trying to change the RMS value of your output, and that is fed to your fan. So you can change the speed by regulating the knob. So AC to AC regulator. So basically, I will teach you these two, AC to DC and DC to AC. So there are a lot of things inside that one. Slowly, slowly, we will try to absorb all these things. Okay, now. Okay, any AC to DC converter here, you can have a look of this one. So if the power AC is going to through the converter and output is the DC, so this is we call it rectifier. And if you can feedback the power to the input also, then this power is we call it inverting loop. We will go details of all these things. I don't want to spend money. So like this one, they have used here. They have used the energy storage. So energy storage element here. Okay, this is the energy. This is one converter. This is another converter. I'm trying to go a little fast. So this is the almost end of the chapter 1 from the net one. I am following the net one. You must understand this one. And at the introduction, I told you have to solve these two problems very clearly and make sure that you understand the problem, because this time, of course, I will change the numbers. I will change this number in the question because it's copied. So when I will set any one of this question in the exam, of course, I will change this data. So you practice and try to understand. If you don't understand, inshallah, you come back or try to make you understand this thing. The extra classes, problem solving classes. So let us go to the chapter 2. The name of the chapter is the overview of the power semiconductor switches. As I told earlier, power electronics is the power electronics. We shall use the device. Use the devices as a switch, as switches. Grammatically, it should be as switches. So not in the active mode or amplifying mode, we shall use this power electronic devices as a switch. So the basics in this class, we shall basically use 3 switches. One is the diode, another will be say BJT, maybe another will be say MOSFET, another could be a thyristors. Are you familiar with the term thyristors? Thyristors basically SCRs.
Sir,
Said, yes.
this kind of electronic devices, we have heard the name, but we don't know what it does. And
Okay.
the function.
Sir, is it the device which sometimes works as a perpetual system?
Perpetual system means?
I mean, when we give a voltage or a current flow, then it keeps continuously flowing. I have seen a YouTube video regarding.
Yes, actually, yeah. Actually, particularly at this SCR or tracks, all these things, you can control the flow of current. Like diode, you don't have control, right? When it is forward bias, then the current will go. When it is reverse bias, it will be open. But the BJT or MOSFET or thyristors, so that you can control the flow of current. When you want to turn it on, it will turn it on, and you can make it turn it off. You can control the switching by applying the control signal. Like like a BJT. I have already given you some idea. So you have the control mechanism here. So when the both junction are forward biased, so this is N here. So suppose this is collector, this is your base, and this is your emitter. So when both junctions are forward by this voltage, so this will work as a switch. On position is on. When there will be no signal or reverse signal, then this will be off. In the thyristors family, there are some devices. We call it SCRs. I shall give little details, not very details, but little introduction. So this SCR will be turned on when we shall apply a voltage to a particular terminal. It is a three terminal devices. So anode and cathode will apply the voltage, and there will be control signal that can be applied to the gate. So I shall come with it. Let us. Okay. Presently available parts devices can be classified in the three groups according to the controllability. So diodes. Diodes are the switch you can turn on and off actually by the power circuit. You cannot make it. When the, okay, suppose I'm giving some example. Are you familiar with this one?
Yes, sir.
So this is your input. Suppose this is your input supply voltage or input voltage. When this voltage is positive, this is forward pass, that means you can signal the switch, and then there will be current. This current will be say I will be a by I, by R. And when it gets the reverse bias, then the switch will be off and there should not be any current. So this diodes are then you don't have an in this diode. Okay, in this diode, you don't have any control mechanism to change the magnitude of your output. It is fully dependent on the input voltage. And also when you are switching, so and this diode will be switched on when you will get the forward voltage, and it will be switched off when you will get the reverse voltage. Okay.
Yes, sir.
Okay. Now, thyristors. So it is so what they say. It is on-off state controlled by the power circuit. Thyristors. Thyristors latched on by a control signal and but must be turned off by the power circuit. What does it mean? Okay, let me give you the symbol, at least you should know. So this is the symbol of SCR or thyristor. Thyristors, I told you, it is a family name. Under this one, there are some SCR, stripe, diag. There are some light control thyristors. There are some other. Okay, I'll show you these devices. At least 20 or 30 types of devices for this category. So, okay, this is your anode, this is your cathode, and this terminal is known as gate. So actually, if you, I'll show you the characteristic. If you make it forward bias, the current will not go unless you apply a gate signal. When it gets this gate signal, then only these thyristors or SCR will turn on. Otherwise, it will be turned on. But as they mention it, okay, latched by a control signal. Latched by a control signal means that it will be turned on by a control signal. This control signal will be applied to your gate, but it will be turned on forever unless you make this voltage reverse bias. If you make it reverse bias, then only this thyristor will be turned off. Otherwise, it will be turned off forever. But then on the third category switches are the turn on and turn off by the control signal. This is like your BJT MOSFET, where there are some gate control thyristor. We call this gate turn off thyristor. So you can send a reverse current to turn it off to your gate. So that this is the controllable switches. Controllable switch, we want this controllable switch. We want to turn on and turn off by myself, by the operator. or by the some of the auto signal. But these diodes, as I mentioned, that we don't have any control over this one. This will be on and off by the applied signal, and thyristors will be also turn on and off if it is S here particularly. Turn on by applying the control signal, but turn off will be done by the power circuit. That means what is the circuit you have applied? If you make the reverse bias voltage is applied across the anode to cathode, then it will be turn off. Okay. So okay, diode. So do I need to discuss this diode characteristics? Hey, who
No,
taught this?
Yes, sir.
Yes, sir, this is pretty clear, sir.
It is clear, okay. So this is the ideal characteristics. They call it idealized characteristic. And if any for this diode, if ideal, if remember I taught you, right? If a 0 plus voltage is applied, then current will flow like this, and this current can be controlled by applying by inserting any current limiting resistance. And when the reverse bias voltage, that is the negative voltage, is applied across this diode, then there will be no current. This current will be. That means turn on. Turn off this circuit. Okay, this is the symbol of your circuit. I'm becoming thirsty. Okay, the very interesting thing is, okay, there are mainly three types of diodes. I think you should know all this thing. Actually, we should read it. Have you heard the name of the Schottky diode?
Yes, sir.
What is Schottky diode?
Sir, I don't know the details, but it has a lower voltage drop as far as I know.
Yes, right.
So
And
it
you know
uses the Schottky barrier for
yes, barrier potential is less.
barrier for the
3 volt, and it is actually you don't have the PN junction, rather than say
metal.
P is there, P is there, and the metal is there.
Metal is
That is, and then it is switching. You can switch it very quickly. Why? I'll come up
so
right now after 1 or 2 minutes. There are first recovery diodes. So these are designed, the doping is designed in such a way that you will turn on and off very quickly. So why I am talking it quickly? Why it is not turning on and off like instantaneously? I'll come back to this. And line frequency diode, these diodes are operated in your 50 Hz. Okay, so I'm not going very details of the Schottky diode, rather than let us say someone why I'm talking about that first switching or reverse, they call it reverse recovery, first recovery. What does it mean? Okay, so we will go little details later. So if you look here, the diode current is now positive. This is the positive diode current, right? Positive diode current. So we turn it off by say the forward bias signal has been removed, but then the current does not go 0 immediately right here. If it go immediately right here, we would be very happy. But because of the there are some carriers inside the diode material that will not allow to make the current 0 immediately, rather than it takes some time. Because there are some, you know that the current through the PN junction that will be contributed by the flow of the holes and the electron. So when you switch off, so it takes some time to recombine this free electron. So it takes some time to make this kind of 0. So if it is 0, then we will be happy. Oh, our switch is off, diode is off. No, actually that never happened. What happened? This current goes to the negative, practically. Goes to some negative value, we will have some problems or details, these things, inshallah.
Sir, is it for the capacitive effect of the PN junction?
Yes, yes, you can say.
Yes, last semester there was a reverse recovery time.
Yes, reverse recovery time. Actually, what happened? There will be two types of 2 reasons. There are some areas that is situated or that is staying in the other than PN junction, bulk of the semiconductor factors, they need to be utilized. And also there are some the same PN junction, majority minority areas in the PN junction area. So that those also need to be utilized. So the we will define two regions later, inshallah, and then we will say that this is because of some of the reasons, this is because of some of the reasons. I'll come back to this. But the real thing is that look here, the current goes to the negative and it has a maximum value of the, we call it the reverse current. Reverse current will have the maximum value. Then slowly the recombined process going on, and then finally the current will be zero. So this is actually the we call it reverse recovery time. This is your reverse recovery time, and this area they call it reverse recovery charge. So what is the area of why this is known as charge? Because this is time scale and this is your current scale. This is your current scale. So this is the area will be nothing but the half. So if it is a rectangle, half TRR multiplied by IRL. So what is this one? Current multiplied by time is what? Current multiplied by time is what?
Charge.
Charge.
That is why it is known as they call it reverse recovery charge. Okay, we will come back, inshallah, with some mathematical things. So look here. So diode does not go to, it is not off here. It takes some time. We call it reverse recovery time. This is the reverse recovery time. So if this reverse recovery time is less, then we call it first recovery time. If it takes long time, these are not first recovery time. Why? This reverse recovery time gives the limitation of turning on and off of your diode quickly, because you must wait for your current. When you turn off, it was turned on, here the diode was on, but when you make it off, it does not go to off position, rather than it takes some time. So because of this reverse recovery time, diode is not fast to go to the off position. So that is why we call it, its switching time is very high. Switching frequency, it is low. You cannot switch on and off very quickly. But our sometimes in some cases we want that it should be turned on and off very quickly. Although it is, I am giving the example of diodes, but it is also true for other electronic devices what will be used in the power electronics. Okay, I am coming to your this thyristors or SCR. So look here, this is the characteristics, VI characteristics like your diode. So okay, this is the I have already shown you the symbol. This is your anode, this is your cathode. So we shall apply here. Okay, let me draw some. So you have a variable voltage. What is the biasing condition of this thyristor? If this is anode and if this is cathode. What is the biasing condition? Look, anode is positive with respect to cathode. Forward. So, but if you apply, if you increase this one, now if I want the current, say IA, so you will not get any current. There will be no current, because this one is fabricated such way that unless you give any signal to your gate here, there will be no current will be zero. Now, then what will be your, if it is your output voltage is zero? Now I am trying to plot it with just time. So what will be the output voltage here? If we don't give any gate signal, just we have made the this one forward bias. There will be no current. If there is no current, what will be your voltage V0 will be?
Zero.
Zero.
I0 R. So if I is zero, so we will not get any voltage output. Now here, suppose here, intentionally we have applied a signal. We call it gate signal or firing signal. This is very important. T1. We have applied an IZ here. That means signal has been applied. We will go a little details of the structure because this one is the, we call it PNPN. So if we apply a voltage here, positive voltage. So this junction J1, this is your J2, this is your J3. So this junction is forward bias, this junction is forward bias, but this one is reverse bias. But if we apply a say a signal here, if you push some current here, then this one is also forward bias, which is broken, and then on the current will flow. So when we apply this voltage, this current IZ, the gate current here, then all this junction will be forward biased or broken, I should say, and then there will be a path to flow the current. Then it will be short circuited and current will flow. If the current will flow, then what will be your output voltage V0? During on. If it is on, then what will be your output voltage? Apply Kirchhoff voltage. Are you listening to me?
Yes, sir. It is IR.
Yeah, it is IR or it is simply Kirchhoff voltage law. Your V0 must be equal to E.
EV, yes.
Am I correct or wrong?
Yes, sir. You are correct.
It will go like this. Unless you make this voltage reverse bias, this current will continue to flow. Okay. When you will take this, please wait. Vice Chancellor called, please wait. Okay, I came back. Now, since this current will be continue and it will never be turn off and it will be continue up to Qiyamah, so you have to make it turn off, right? How can you turn off? What I told you. How you want to make this current zero?
So we will have to apply reverse bias.
Yes. So this is as they told you by applying the external circuit mix. Either you will take this. Okay, let me use the eraser. I don't have duster. Oh, I miss my class. Just to you either you have to take out this voltage, or you have to apply reverse bias. Like this. Then only current will be zero. You got my point?
Yes, sir.
But, okay, but there is another device, thyristor, like this. You can apply a reverse current. We call it GTO. What does it mean by GTO? I told you. What is GTO? Gate turn off receivers. So these are fabricated like that. If you apply a negative current here in the gate, then it will be turned on. Okay. So if we get this type of device that we can turn it on and turn it off by myself, so we have the full control, right? You got my point? What I say?
Yes, sir.
Hello. You have to, yes, sometimes say yes, sir. Otherwise, because I cannot see your face, I want to do something. I am using another computer, so I want to see your face sometime. I don't know how to do that, because when I am showing, when I'm sharing the screen, that comes side by side, but say 50 students, it is not much. Okay. Okay, so this is the example they have given to you. So it has also this same problem. Can you see my cursor?
Yes, sir.
Okay, so okay. Look here, this thyristor also takes some, when it is turned off, it will not turn off very quickly, rather than it takes some time. Okay. So when your thyristor is turned on, what should be the voltage across your thyristor? When the ideal, this is your G. If it is on, then what is the voltage it should be?
The supply voltage.
Yeah,
Sir, in the
on short circuit.
Oh, sorry, it is short circuit.
If it is short circuit, then voltage should be what
Zero.
is the zero? Yeah, that is why they say that the voltage is zero. Look here. Now they have given a say reverse bias voltage or something like that. So still so this GFA is going to 0, 0, 0, 0, 0. And it should be actually the applied voltage, right? But that will during this TRR, it has a reverse voltage and then it goes to 0, and then only the device is said to be turned off, but still it takes some time to get the full recovery voltage. Okay, I'm probably you did not understand what I said. Just showing. Okay, so suppose this diode is open, right? This one is open. And let me draw it. If it is open, what should be the voltage?
Supply voltage.
Supply voltage. But look here, as we have already shown to you, this is the sub negative voltage should be, or this the negative voltage is the voltage supply voltage. This is your supply voltage. So that does not come very quickly, rather than it takes some time. So this switching on and off, it is not practically, it is not being done immediately, rather than it is taking some time. So we want to check what is the time, what are all these things.
Sir,
So yes.
sir, since sir, in the graph we can see that the current takes some time and the voltage takes some times. So since there are some current and voltage, is it something related to the switching loss?
Yes, I am going to that point. So you just read it, okay? Study, just read. So okay, yeah, very intelligent question someone has asked. So I'll go to that. So before that, let me tell you, so you read it 2.4. What are the desired characteristics in a controllable switches? Controllable switch means it will be turned on by you, and also it can be turned on by you. So we want that this is the switch. We want that when it is off, it should when it is on, clock arbitrarily large forward and reverse voltage. When it is on, it should lock it. It should not be broken down. And when the reverse voltage is applied, there should be zero current and there should be not any breakdown. Ideally, what we want to say is that when it is on, the voltage should be zero. When it is off, the voltage should withstand the reverse voltage. Conduct arbitrary large current with zero voltage drop when it is on. That we want. Practically, we will not get switched from on and off instantaneously, but practically it does not happen. There is some reverse recovery time. Vanishingly small power required from control source to trigger the switch. So if you want to get the gate signal in your thyristor, it should not take large power. If you waste a large power to generate this control signal, that will be loss, real loss. So this control signal should not take much power. Actually, you have already learned the op-amp. Have you all learned op-amp?
Yes, sir.
Yes, sir.
So by using this op-amp, you can generate this signal and it will not take it. So the highest voltage will be 5 volt or 10 volt, 15 volt maximum in op-amp. And that is the analog circuits, and the current will be in the milliampere range. So it should not be, it should not take very high power to generate the control signal. This control signal is nothing, in our example, the gate signal to the thyristor. Okay, now in front of you, a figure has been introduced here. This is the figure of, we want to see the switching loss things, as someone mentioned. So this is a DC voltage we have applied, and this is the current source here, and this is the ideal diode, and this is the switch we want to operate on and off. Okay, when this switch is on, then the current is supposed to come like this, right? Am I correct or wrong? When the switch is on, suppose this is on. So this diode will be reverse bias, so this IO current would come this way and this way. And also, when the switch will be off, look here, this current will be flowing like this. Am I correct or not?
Sir.
Okay. So now, if you go to the next figure here, then I should make it, can you see it now?
Yes, sir.
Still. Here. So if it is, if you can see it. So now, this is the control signal we want. This is the control signal we want to control the switch. So look here, this is your T, this is your T axis, this is your T axis, and this signal is negative, means that the switch is off. If the switch is off, then what should be the voltage VT? Apply your Kirchhoff voltage. Because that if the switch is off, then I say that current will be flowing like this. So what should be the, if the current is going like this, and if the diode is ideal, then what will be the voltage from here to here? If the current is flowing through the ideal diode, then what will be the voltage across the diode? It is short
Sir,
circuit.
it will be short circuit, so no voltage drop.
Okay, so then what will be, you apply the Kirchhoff voltage law? What will be your VT? Is it not VD?
Yes, sir.
Okay. So and when the switch is off, the voltage across this switch is VT, and it is going like this. And but you look here, we have applied a turn on signal here, control signal to your switch, and then it is supposed to be turn on like this. Yes, it is turn on. But look here, the voltage should not, if it is turn on, what should be the voltage VT?
0.
0. But it does not go to 0, rather than it is taking some time. We call it TFV. That is the follow-up voltage, time taking to follow-up voltage from a say particular voltage VD to 0. And also the current through it. This current, if it is on, the current should flow like this. And this current is not going instantaneous to I0. It is taking some time also. So this is called, we call it rise time of the current. So look here, voltage also taking sometimes to going to 0, and current is also taking sometimes to build up. So during this time, actually across the switch we have voltage and current. And if we multiply this voltage and current, then what we will get?
Power.
The power loss.
Power. And also here we have applied the, look here, we have applied the negative current across the switch. Then if the voltage should be immediately, the voltage should be built up, but it takes some time. And then also it takes the rise of voltage like this. And also current should fall immediately to 0. No, it is going, and it taking some time to 0. So during the off time, again, there is another triangle. And voltage and current, it will be power loss. So in the on and in the off both side, we will have some power loss, okay? This power multiplied by time, power multiplied by time, what you will get?
Energy.
Energy. So these are nicely given in this book. So please go through it and you will have some problem. And problem means that some numerical problem to solve using this one. So that has been given and the equation has been derived. So please go through this. The all total time is rise time of the current and fall time of when it is on. And then this is the energy during the on time, and this is the energy during the fall time, off time, sorry. And total energy will be this one. And with that one, you will be able to solve problems. And if you make a what is that, the summary, there will be 9 characteristics that should be there in a controllable switches. Please note it, and you may need to write down in your exam. So you don't need to memorize, just you go through, you realize what is it there. So we'll not learn anything from this chapter, and we shall go. There are some characteristics of the other switches like say BJT, MOSFET, you know all these things. So only the thyristor is new to you. So we shall go to the Harun Rashid books and see some of the controllable characteristics. But problem number 2 and problem number 1, this is mainly related to that circuit that we have shown you relating to your power loss, switching loss. Please go through it and try to solve these 2 problems. And again, the solution manual is to you, and I'll surely change the number so that you don't copy it directly from the solution manual that we take some. Okay. So you want me to go more, or you want to move to the next class?
Sir, next.
Speak out.
Yes, sir. The next class. Next class, sir.
Okay. Okay, so look, this is the MCT means MOS control transistors. This is P type, this is N type. So you can control these things, and this is your MOSFETs. Are you familiar with this one? I am very sorry I could not take this class. So I got some complaints that you did not understand very much about the MOSFET thing. So if you have any problem, then I can take one introductory class of MOSFETs. One. But that has to look here. I told you GTO. Didn't I tell you GTO?
Yes, sir.
Yes, sir.
So look here, yeah. So you can turn it on and off by doing this one. Okay. Okay, then. Inshallah, we shall meet after Eid, right?
Yes, sir.
Am I correct
Inshallah.
or not? So
Yes, sir.